Okay, welcome to this lecture on gear efficiency. In this first part, I will give an introduction to the field, and then I will derive some expression for the efficiency of a gear a meshing gear. So, my name is Roland Larsson. I'm professor of machine elements at Luleå University of Technology in Sweden. The content of the lecture is, first of all, we will discuss load-dependent and load-independent losses in gearboxes. We will, as I said, derive a mathematical expression for the efficiency. We will discuss how different gear parameters influence the losses, and briefly about how you can measure gear efficiency, and finally about the friction itself in the gear contact, in the gear teeth contact, and connection to elastohydrodynamic lubrication. But let's start with a simple gearbox, and let's see, where do the losses come from? Well, there are some obvious sources of losses. First of all, the oils are normally lubricated by an oil bath like this, so the lower gear wheels are dipping down in the oil like this, and of course, in order to turn in the fluid, there will be a resistance, and it's a pretty substantial resistance at high speeds. So that's an important source of loss. We call that oil splash. The gear mesh itself, of course, as you know or may know, there is quite much sliding between the surfaces, and that is causing friction and losses, of course. We're coming back to that later. Bearings is maybe not the biggest source, but can still be important, and also normally you have seals to avoid that the lubricant is coming out here or something else is coming in. You also have drag, so this is a very sketchy picture of a gearbox, but as you can see, both wheels can't be engaged at the same time here. So one of them are just following, so there is a bearing inside here, so for that reason there will be some drag, and all the gear that is not connected. And even windage can play a role if you have high speeds, so the wind resistance can give it a pretty high loss. So, in general, of course, gears of this type, spur gears and helical gears, the efficiency is very high. Normally, it's in the up to 99% or even more. But since gears are so efficient, they are also used to transmit very high power. So even if 1 or 2% is lost, that is a substantial amount of power. So if it's possible, we can try to increase it even more, the efficiency. And I will discuss now briefly two types of losses. That's load independent and load dependent. Starting with a load independent, that's the losses that they may vary with speed, for example, but they don't vary with load, of course. And typical examples are those I already mentioned: bearings, seals, the synchronizers, the drag in that, but also the things around the gear, like the churning loss, the oil splash, windage, trapping and squeezing. That's when the oil is trapped in between the gear teeth. If you have plenty of oil there, it must be squeezed out, and that takes some energy too. Also, if you have jet lubrication, that will also cause losses when the lubricant is thrown away. So And these type of losses, they are influenced by the geometry, for example. So the flows inside are important. It's also very important to how much oil you put there. If you have a very high level, oil level is high, you have a high oil splash. Rotating speed, definitely big influence. So the higher the speed, the higher the loss, and the viscosity and even density play a role. So viscosity play a role because the oil splash is becoming more severe if you have high viscosity. So many manufacturers of gearboxes, such as those in automotive industry, the current trend is to try to reduce the viscosity. That may lead to other problems in other places in the gearbox, such as those you may increase the load dependent losses instead. And the load dependent losses, they are increasing with increasing load, and the main source is of course the contact itself, the contact between the gear teeth, and of course you can try to modify the shape of the gear teeth, and more important maybe, you can try to reduce the friction coefficient between the gear teeth. The friction coefficient of course depends very much on the lubrication, and if you have been able to reach a full film lubrication regime. So the trend here is to try to reduce the friction coefficient. It could be by improving the lubricant, using other better lubricants, could be to make better surfaces, could be use other surface treatments like coatings, etc. So at the moment today, there are plenty of activities to reduce the losses in transmissions. And maybe the Stribeck curve can describe a little bit what we want to do with this, with the friction coefficient. So this is the Stribeck curve in the different regimes, and we really want to push this curve in towards the lower left corner. That means we want to reduce the friction in the boundary lubrication regime, and we want to move the shift from boundary to mixed further to the left. That means that we can allow thinner films still getting a full film lubrication. Now, I will now focus a little bit on the losses in the gear mesh itself, and this type of loss is of course very important for highly loaded gears, and the reason why there is a loss, first of all, is the sliding motion that takes place. You may remember the gear, how the gears are interacting, and you may see from this picture that the surfaces slide. It's not very easy to do that, but coming back to that, but they slide and they partly roll and they slide again. You remember also gear geometries that you have the base circle, you have the pitch circle. Pitch circle is the corresponding radius of the two wheels rolling in contact with each other. Base circle is the circle from which the line of action is unwound from the run wheel to the other one. Coming back to that very soon. When we talk about friction in EHL or in gear contacts like this, the friction coefficient varies with the slide to roll ratio in this way. This is a typical U slip curve at full film lubrication. The slide to roll ratio is a measure of how much the contact is in sliding motion and how much it is in rolling. So if one surface is moving with U1 and the other one with U2, the average speed or the entrainment speed is simply the average of the two velocities. The slide to roll ratio is the difference is the ratio between the speed difference and this average speed. So the higher the slide to roll ratio, the more sliding it is. And if you go up to high slide to roll ratio 2, for example, you have pure sliding, you have no rolling. If you are down here 0, you have just rolling motion, and then the friction is very low. So this is a typical behavior, that the friction increases very rapidly when the surfaces start to slide, reaches the maximum, and then flattens out, but then goes down a little bit due to thermal effects. Okay, now we'll do some mathematics to learn how the losses occur. I mean, what are the important parameters in the gear? And it's always nice to have a mathematical expression for that, because then you can see the importance of different parameters. Coming back to the Involute gear, as I said, you may remember how it works, but it's a very smart invention, this Involute gear. You remember that you start from two base circles like this. You can see that you can look upon the gear as a wire unwound from one surface up to the other circle, and that means that you can have a constant transfer of torque and speed. So if you have a constant input from one wheel of torque and speed, you have a constant torque and speed on the other circle too, or the other wheel too. And this wire, which is unwound from one to the other one, is called the line of action. You remember that. And this is the base circle of the two wheels. Okay, now what we want to know is how much the contact point is sliding. I mean, how much sliding motion is there in the contact point? And because the sliding will also cause losses. So this is now we have it's a kind of sketch here, schematics of the gear. So here is the center of wheel 2, here is the center of wheel 1. Here is the line of action, and here is the contact point at the moment. So at the moment the gear teeth are in contact in this point. And starting then with the first getting the velocity components here. So we have velocity components that are normal to the gear flank, and those who are transversal to it. These are the sliding speeds. So one gear tooth is moving this speed, and the other one that speed. So the difference here is the actual sliding speed. In this direction the speeds must be the same, because they are following each other, and they move in contact with each other. And these two speeds, they must be the same, as I said. They are simply RB, the radius of the base circle, multiplied by the speed, rotating speed, and that must be the same as the base radius multiplied by the speed of the other circle, because this is the speed of the wire. This is the speed of the wire that is constant. It must be constant all the time. Perpendicular to the line of action, it's quite easy also to define the speeds, because you can see this as something that is rotating, and you can actually move this point into that center without losing anything. And of that reason, it's quite easy to see that this speed must be this distance multiplied by the rotational speed. You can stop the video and think about that for a while. This radius multiplied by that rotational speed gives you the velocity component for wheel 1, and the same thing, this distance n2p multiplied by the rotational speed of wheel 2 must be the transversal speed of wheel 2. So then you have the two velocities. Okay, let's move on. So the difference in speed, that's the sliding speed, is simply the difference, and then we need to know the distance np here for both cases. We can split the np distance for wheel 1 and wheel 2 into two parts. It's the nt distance plus the pt distance, and the n to p and the pt. And since this distance, these two distances multiplied by in this point, which is called the pitch point, there is rolling motion, and of that reason, when p is here, so that means that pt is 0, we know that delta v should be 0. So putting pt 0 here means that this should be 0, and then also n1t omega 1 must be equals n2t omega 2. And making use of that expression into that one, we can see that the speed difference, the sliding speed, is simply pt multiplied by the sum of the omegas. And pt is simply a coordinate along the line of action for the contact point at the moment. So pt is varying from somewhere here to somewhere here during the engagement. Okay, stop the video and think if you need to think over this. Okay, and then now we know the motions. Next thing is to determine the forces, because we need the forces or the torques, and we need the motion, because the torque multiplied by motion is power. Okay, forces then. Again, line of action, center of wheel 2, center of wheel 1. Contact point here. The contact force is split into two parts. The normal force in the transversal plane. Now we can assume that this could be an helical gear also. If it's a spur gear, it's simply the normal force here. And we have also the friction force. And the friction force is the total force Fn, the total normal force, multiplied by the friction coefficient. It's a total force since the sliding takes place in the transversal plane, and all friction is in that direction. So the total force in the contact point is here then, and it has a angle to the normal force, which we call rho. So torque equilibrium, then we can set up expressions for the torque around the center of wheel 1 and around wheel 2. So the torque here will be the force F multiplied by the length of the lever here, which must be RW1 plus delta. So RW1 is the pitch radius of wheel 1. Delta is a still unknown distance here, which occurs because of the friction here. If you didn't have any friction, the delta should be 0, and you should be in the pitch point here. And multiply by the cosine term to adjust for the angles here. Again, stop the video and think over these expressions that they're okay. It's the same thing for wheel 2. Here it's pitch radius for wheel 2, but minus delta, of course, because we are below the line of action multiplied by the cosine of the pressure angle minus the friction angle rho here. And the friction angle rho is simply the friction force divided by the normal force. And since there is a ratio between the normal force and the normal force in the transversal plane, which is simply the cosine of the helix angle, tangent rho is mu friction coefficient over cosine beta. If you don't remember the gear geometry parameters, I strongly recommend you to read about it and go back to the video later. Okay, now efficiency. From the previous slide, we had the torques here, and efficiency is simply the power out divided by power in. So power out is torque multiplied by speed, rotational speed, and again torque divided by torque in, or rotational speed in. That means making use of this expression, we end up with this pretty simple expression. We can simplify it or rearrange it a little bit, and we end up with something like this. And now we can see that this delta is a small distance in comparison to the pitch radius, and making use of some simplifications, typical simplifications in mathematics. If we have a small epsilon 1, epsilon 2 here, that means that we can approximate it as 1 minus the sum of these two epsilons. So we end up with this expression. So the efficiency is simply this distance multiplied by the inverse of the sum of the inverse of the pitch radii. And this also means that the efficiency varies along the line of action, because this offset delta is not constant all the time. It depends also on the friction. So now we have to define this parameter delta. As I said, it depends on the friction because it depends on the angle rho here. And now we can make use of the sine law. You remember that one? That tells you that the distance, if you have a triangle here, that means you also have rho angle here. So the ratio between the distance here to the sine of that angle must be the same as the ratio of this distance and the sine of that angle. And this angle is 90 plus the pressure angle minus rho. Stop the video again and think over that. You can simplify that. Sinus 90 here can be made to cosine instead, and you end up with this expression. And also, if rho is a small number, which it is, then you know that sine rho is about the same as rho itself. So you can simplify it to in this way, and you get a nice expression of the delta. So it's rho, the angle, multiplied by the coordinate pt, which is the coordinate of along the line of action. It's a variable, divided by cosine of alpha wt, which is the pressure angle. And you can also then make use of the previous this expression, and you end up with something like mu multiplied by the coordinate divided by the cosinus, the helix angle, and divided by the cosine of the pressure angle. So here you can see if you know the mu at the point, but then you remember also that it varies with mu is varying very much with how much sliding that takes place. So you have to think over that too. Okay. So putting everything together now, you can putting in the expression for the delta into the equation for efficiency, you end up with this one. So efficiency is 1 minus something. So the bigger this something is, the more losses we got. And you can directly see here what is influencing efficiency. Well, in a way, PT, I didn't mention that, but the PT, the coordinate, is influencing. The bigger the PT is, the more losses. That means that you have more losses or more sliding in the beginning and the very end of the engagement of the gear teeth. But you can also see that the bigger the mu is, the, not surprisingly maybe, the lower the efficiency. The bigger helix angle, the bigger losses. You can also see that the angle of action or pressure angle is influencing this. It's normally doesn't vary very often, so you may not do very much about that. But also, maybe more important, the gear wheel size plays a role, since the pitch radii play an important role here. So that was the end of part 1, and we will take a closer look on this equation and what it means in the next part. Thank you very much.